welcome to section 5.5, applying the remainder and the factor theorems. We've been working with polynomials through chapter 5, looking at factoring, various ways of factoring. We've been talking about how we can graph polynomials that are of higher order degree through the use of in behavior and then some t-tables or synthetic substitution. Today what we're going to look at are two important theorems that are going to help us with that graphing process. It's going to allow us to find zeros of a function and factors of a function so that I can, one, write my polynomial in the factored form, and from that, set my polynomial equal to 0, and then find the zeros of the polynomial, and it helps me draw what's going on the middle side of my graph versus on the in behavior side of my graph. All right, so we're going to talk through the process of long division today and synthetic division of polynomials. And before we do that, let's review the long division process. When we divide a generic number back in middle school or elementary school when you were just learning long division, when you would divide a number by another number, sometimes the number you were dividing into would go into it evenly and you'd have no remainder. Other times you would have a remainder. And all of those parts, we want to make sure we're familiar with what they are called. So we have in the polynomial world the same type of a situation. We have f of x, and the f of x would be what would be known as our dividend. And then we have a number that we're dividing into f of x, and this is known as our divisor. And then we have q of x, and this is known as our quotient, part of our answer. Then we have r of x, which is known as our remainder. And then we see d of x again here, which again is our divisor. So when we're working with polynomial division, we're taking the polynomial f of x, we're dividing by another polynomial d of x. From that, we're getting a quotient polynomial q of x, and then may or may not have this plus remainder polynomial divided by divisor polynomial. Let's see how this plays out in the number world, just as a refresher for long division. And then we'll go ahead and do some long division with polynomial. So let's say we have 335, and we're dividing 335 by 4. So in our example up here above, where we have f of x, d of x, the 335 would be equivalent to our f of x. There's our f of x. And the 4 would be equivalent to our d of x right now. All right, so we go through the process, and when we were doing long division, we would ask the question, okay, how does 4 go into the 3 in the hundreds place of 335? It doesn't. So then we moved down, and we went to the tens place, and we went, how does 4 go into 33? Well, we can get close to it, but not exactly equal to it. We can multiply 4 by 8 and get a 32. And then what we did was we subtracted that value. I'm going to put parentheses in here just to remind ourselves that we're subtracting. It's probably more important that we have the parentheses when we're doing the polynomial division versus this number division. All right, then we subtracted and we got a 1, and then we dropped down the next number. And now what we did was we treated the 15 as if it was the dividend again. And we're asking the question, well, how does 4 go into 15? Well, 4 goes into 15, it gets close 3 times, because we have a 12, we subtract that 12, and we have a 3 left over. So, we are now left with 83, which would be equivalent to our qx polynomial, that's our quotient. And then we have 3, which is equivalent to our remainder, that's our r of x. And we would write this as a couple different ways. We would have maybe written it like this, 83 with a remainder of 3, or 83 and
good morning,
3/4. Or we wrote it as 83.75. So this is the way, it's 83 plus the remainder over the divisor way. That's how we're going to write our polynomial problems. So there's a numerical example of doing long division. Now we're going to do the same process with polynomials here. All right, so we have f of x, divide f of x by this polynomial x squared minus x minus 2. So the x cubed plus 3x squared minus 7 would be our dividend, and the x squared minus x minus 2 would be our divisor. So this is, back in the example above, this would be our f of x, and then the other one would be our d of x. All right, so we set this thing up. Now we notice in the f of x function that x to the power of 1 is missing. I don't have an x to the power of 1. So I'm going to replace all of my missing powers with a 0, just like we were doing with synthetic substitution. So we set this thing up. We got x squared minus x minus 2. There's our divisor. And we're going to divide that into x cubed plus 3x squared plus 0x minus 7. Okay, here we go with the long division process. Now, when you're doing long division of polynomials, you're always asking, what do I need to do to the lead coefficient or lead term of the divisor to make it look like the lead term of the dividend? How do I make x squared become an x to the third? Well, I need to make x squared become an x to the third by multiplying by an x. And that's the kind of the same question we were doing up here on the number problem. How did I make 4 become a 33? I multiplied by 8. So we're going to multiply this by x, and I'm going to put my x here above my x place of my dividend. And now what happens is we multiply through distribution. We multiply x times x squared, and then times negative x, and then times negative 2. And I get x to the third minus x squared minus 2x. And then I'm making sure, as we did over in that example problem, that I'm subtracting. Now, 3x squared plus x squared gives me 4x squared. 0x plus 2x gives me 2x. And now here comes 7 that drops down. All right. This 4x squared plus 2x minus 7 is now like my new dividend. And I ask the question again. What do I do to x squared to make it look like 4x squared? Well, I multiply by 4. And now we redistribute that 4 into x squared minus x minus 2. So we would take all of these arrows that we've got going on here, get rid of these guys, and show that we're going to redistribute, this time with the 4, so 4 times x squared times x times negative 2, and we get 4x squared minus 4x minus 8. We're subtracting this value here. And we get 2x minus a negative 4x, or 2x plus 4x, negative 7 minus a negative 8, or negative 7 plus 8. And now this is now my remainder. So this is my r of x polynomial. And we have a remainder. We have above the x plus 4. That's my q of x polynomial, my quotient polynomial there. So if we write it in the correct format, as is illustrated here, we would say my answer is going to be q of x plus r of x over d of x. Or x plus 4, my q of x, plus my remainder over my divisor. And there's my answer for the long division of that polynomial by an x squared polynomial. All right. We're going to keep trying some other ones. So this is where you pause and hold and come back and check your work. But I'm going to go ahead and work through this one. We have x squared plus 2x plus 4 going into 4x to the 4th plus 5x squared minus 9x plus 18. X squared goes into 4x to the 4th. I need to make that x squared multiply by a 4x squared. Forgot my missing term here. I'm going to replace my x cubed term. So plus 0x cubed plus 5x squared minus 9x plus 18. There we go. All right, so back to action here. 4x squared. And then we have 4x to the 4th plus 8x cubed plus 16x squared. I'm going to subtract all of these values here. Negative 8x cubed minus 11x squared minus 9x. And then my next setup would be, how do I make x squared look like a negative 8x cubed? Multiply by a negative 8x. Get a negative 8x cubed minus 16x squared minus a 32x. Once again, subtracting. Negative 11 plus 16 is 5x squared. Negative 9 plus 32 is 23x. And down comes the 18. And our last attempt here, we've dropped our last number, so how do I make x squared become a 5x squared? Multiply by a 5. 5x squared plus 10x plus a 20. And once again, subtracting gives me a 13x minus a 2. All right, I have all of my appropriate polynomials. My 4x squared minus 8x plus 5 quotient polynomial. 4x squared minus 8x plus 5. I'm going to add to it my remainder polynomial of 13x minus 2 and divide that by my divisor polynomial of x squared plus 2x plus 4. There's my solution. Okay, let's try the same process now, but through the use of synthetic division. Now, when we do synthetic division, we have a couple things that are kind of some constraints we need to think about. Synthetic division, our divisor must be a linear binomial with a lead coefficient of 1. Lead coefficient equal to 1. That's kind of the restriction we have on doing the synthetic division process. So let's just make sure that that's the case. But it is very fast. It's quick, much better than the long division. The long division you can work out for any polynomial, but synthetic I have to be careful that I'm only having a divisor of lead coefficient value of 1 of a linear binomial. All right, how do we do this with synthetic division? It's the same process as when we were doing synthetic substitution a few sections ago. So I look at my divisor is this x plus 3 polynomial. My dividend is this 3x cubed plus 17x squared plus 21x. And we set it up with just the coefficients. 3, 17, 21, negative 11. Now, what goes out in front? So my divisor is an x plus 3. And we're going to learn here in just a second that generically it's this. X minus k, such that my k value is what I'm going to use as my divisor. And so that means if I have an x plus a 3, it's the same thing as an x minus a negative 3. And so there's my k value. That's the divisor number I'm going to use out front here. We go ahead and drop, we multiply, we add, we multiply, we add, we multiply, we add. This is our remainder. This is our divisor. This is our quotient. So, this really means 3x squared plus 8x minus 3. Now, how did I know it was 3x squared? Well, the polynomial, the original dividend, started as a power of 3. And I'm taking a power of 3 and I'm dividing it by a power of 1. So if you had x to the third over x to the first based on our exponent properties, that would give me an x to the second. And that's how I'm getting that. I'm always decreasing by 1 power. When I use synthetic division, I will always decrease by 1 power if each process of synthetic division takes me down 1 power. So I started cubic and now I'm at a square. I now have my information to be able to write my answer here. I have my quotient, 3x squared plus 8x minus 3, plus my remainder over my divisor. Well, my remainder just happens to be negative 2. And my divisor, again, was the x plus 3. So this would be my solution, or my answer, for the division through synthetic division process of that example A. Let's try another one. Making sure that everything's working. So here's my, quote, x minus k value. And that means I've got an x minus 3. So my k is equal to 3. Just think of the opposite that you see in that binomial. So I'm going to have my dividend of 2 and 9 and 14 and 5. And again, I'm going to be careful and replace any missing terms with a 0 there. And my 3 is my divisor. So multiply, drop, multiply, add. There's my remainder. Here's my dividend. So we have, in this case, 2x squared, because it started as a cubic, plus 15x, plus 59, plus a 182 over an x minus 3. There we go. Very efficient. Whole synthetic division process. All right, here's our first of 2 theorems we're going to look at for this section. It's called the remainder theorem. If a polynomial f of x is divided by a binomial x minus k, then the remainder is r equal f of k. So this, there's my remainder. And again, that is f of 3. So 182 equals f of 3. Well, we learned a couple sections ago that actually is helpful to me in a couple different ways. One of the ways it's helpful is it tells me I've got a coordinate of 3, 182. That's a point on my graph. But the remainder theorem is just stating the fact that the last number I see in my synthetic division process is the remainder, given this value of k that I plug in here for my function. All right, so make note of the remainder theorem. You're going to like this thing, especially when that remainder ends up being a 0, because then we get to talk about the factor theorem. And here's what the factor theorem says. If our remainder is 0, when our polynomial f of x is divided by this x minus k value, look what happens. If your remainder is 0, your remainder polynomial is a 0, 0 over x minus k, that whole thing just goes away. And I end up with just my quotient. Well, you and I both know that if I take a polynomial or a number and divide it into another number, and it just so happens that I don't get a remainder, that we have found with this divisor right here, we have found a factor. And that's the same thing that's happening with the factor theorem. If I take a polynomial and I divide by a binomial of x minus k and I get a remainder of 0, that x minus k is one of the factors of my polynomial. So this remainder of 0 idea is a great thing. And I want to find that because it helps me find out factored form, it also is going to help me find zeros. So that's the factor theorem. Polynomial f of x has a factor x minus k if and only if that remainder, if the value of the function is equal to 0, if my remainder is equal to 0, then I know x minus k is a factor. Very crucial concept here for us to understand. This is going to help us with the factoring. It's going to help us with the graphing of these polynomial functions. All right, so the factored form helps you find the zeros of your function. It's doing so because it allows you to set the function equal to 0 and then find those x-intercepts. All right, let's see what happens here. We're going to factor completely, given some polynomial x minus a k, and that x minus a k, now this is key here, it tells us that it's a factor. So if I know it's a factor, my remainder should be 0 when I do this problem. So here we see our x minus k is a 3, which means our k that I'm using in synthetic division will be positive 3. So we set up synthetic division. 2, negative 11. Again, being careful if there's any missing terms here. We're going to put a 3 out there. We're going to drop and multiply. Get a negative 5, negative 15, negative 12, negative 36. And yes, we ended up with a remainder of 0. That's good. That tells us that this was a 0. More importantly, it tells us that x minus 3 was a factor. It confirms that for us. But then what do? Because I'm supposed to write this thing in factored form. And so far, all I know is that x minus 3 is a factor of that polynomial f of x. Well, what about the other possible factors? Well, remember, synthetic division process takes us and it breaks us down 1 power at a time, this polynomial. So now this 2 minus 5 minus 12 is actually 2x squared minus 5x minus 12. That, we have kind of one of 3 goals in using synthetic division. To find zeros, to find factors, and to get myself quadratic-wise, to get my polynomial to become quadratic through the use of synthetic division so I can factor this thing, hopefully. Let's see the factors. 2x and an x. I want a negative 4 and a positive 3. That would factor. And so there are my other 2 factors. So my factored form of 2x cubed minus 11x squared plus 3x plus 36 is equal to x minus 3 times 2x plus 3 times x minus 4. So there's my factored form of my polynomial. Let's try this one. We know that x plus 1 is a factor. That means my k is a negative 1 this time. Setting up 1, 4, negative 15, negative 18, negative 1. Drop it, multiply it, add it. Negative 18, positive negative. Negative 18, negative 1 makes positive 18. And yes, another remainder of 0. So far in factored form, x plus 1 is my factor. Now, we haven't talked a whole lot about this, but you have the potential of having 3 x-intercepts, 3 zeros, real zeros. You might not have 3 reals, you might have 2 reals and 1 imaginary, but you're going to have 3 possible zeros that you're going to have, which means factor-wise, you're going to have possible 3 factors. Well, let's see what we get here. We know that this refers to x squared plus 3x minus 18, and this one factors nicely for us here. Those are my other 2 factors. So I know that x plus 6 is a factor, and x minus 3 is a factor, and there's the factor form of that polynomial. So we can see the factored theorem, the zero theorem at work here. Very useful for us, especially when we're trying to put these things into factored form. Now, why we're trying to put them into factored form? is because we want to find zeros. Zeros allow me to plot x-intercepts, and x-intercepts allow me to help draw the shape of my polynomial when I'm graphing this thing. So when we're finding zeros, as a reminder, that means I want to look for a remainder that is equal to 0. And when I do that, the divisor that I'm testing, that k value that I'm using, that gives me a value of 0 for a remainder, that k value becomes one of my zeros. So there is the relationship between zeros and that 0 helping me write factored form. And this is the relationship you're going to need to know. If you know a factor of a polynomial, you in turn know its 0. Vice versa, if you know a 0 of a polynomial, you will in turn know its factor. So that relationship is critical there. All right, so they're giving us this polynomial, and they're telling us this, f of 4 equals 0. Remember, that's function notation. F of x equal y. They're telling us that if an x is given, I get a y that's equal to 0. And anytime I have a coordinate where my y value is equal to 0, I know that I found an x-intercept, which means I know that I have a 0. In this case, of 4. So, setting it up, 1, 1, negative 16, negative 16. I know I'm going to have a 4. 4, 5, 20, 4, 16, 0. There's that 0 remainder, which we want. What do the other zeros look like? Well, the factored form, if I set equal to 0, helps me find the other zeros. So this is x squared plus 5x plus 4. And if I set that equal to 0 and factored it, I'm going to find that my other zeros are negative 4 or negative 1. So the zeros of this function altogether are negative 4, negative 1, and positive 4. Going back to the factoring idea, if I know what my zeros were, then I knew that my function is x plus 4 times x minus 4 times x plus 1. There's the factored form of that polynomial. They didn't ask us to find that, but that's the concept I need you to get in your head, is that those zeros help me find factors, and factors help me find zeros, so they always work together. They're hand in hand. All right, and then our last example here. There's my k. Set it up. Using that value of k. Bingo. Now I know quadratic-wise, I can set this equal to 0. Now sometimes this is not going to factor, which means I'm going to have to use quadratic formula. And that's okay. I can still find zeros that way. I think, though, that we're okay here. 3 minus 1 is going to give me that 2 value. And then 1/3 or negative 1 are my other zeros. So all of my zeros, including the one that I was given originally, negative 2, negative 1, and 1/3. And there we have it. So some very useful tools for us here with the whole zero theorem and factor theorem. Hope that's helpful.